All right, everybody hear me okay?
Yep.
All right, just making sure I checked in. Everybody see my whiteboard okay?
Yep.
All right, good. So we're all on the same proverbial virtual page. All right, very good then. All right, guys, thinking ahead for next time, which is lab tomorrow, right? So we're doing what? Spectroscopic analysis of iron, is that correct? I hope so, because that's what I prepped. Okay, so everybody found that lab over on D2L. All right, good. So what I want to do today is at least get it started in terms of some background on that lab. Again, it's always a good idea to review what's due tomorrow. So we have a quiz tomorrow, right?
As always.
I wrote that.
Yep.
As always. All right, got a quiz. And that's going to focus on the EDTA stuff, so just be aware of that. I think I also did post some homework, and I've got that due a couple Tuesdays out. That should be up on D2L as well. But as far as what's due tomorrow, looks like we'll have a quiz and then the calcium EDTA notebook, right? That's all that's due tomorrow. Am I correct?
Yep.
Yep, no homework tomorrow. All right, good. So what we're going to talk about today is spectrophotometry or spectroscopic analysis. Spectrophotometry is the study of the interaction of light with matter from a quantitative perspective. All right. So that's actually how we're going to make our measurement today. So just to, again, to give you a basic overview of what it is we're trying to do. The analyte, I always like to do this. The analyte in this case is going to be aqueous iron ion, specifically iron 2+. Okay, so that's what we're trying to measure. All right, and we're going to measure it by looking at how it absorbs light two different ways. So we're going to use two techniques to measure that. First one is going to be visible spectroscopy. So that actually uses visible light. So we're going to be probing the matter, which is iron 2 ion, in this case with light in the visible part of the spectrum. And the instrument that we're going to use is going to be a Spec 20. I'm also going to have another scanning spectrometer in there for us to use, so we can actually determine the wavelength of maximum absorption of the iron complex that we're going to make. The other technique we're going to use is atomic absorption spectroscopy. So in this case, what we're actually going to be looking at is the concentration of the iron atom in the gaseous phase. So we're actually going to make iron atom, and we're going to actually generate a vapor of it in a flame, and we're going to measure the concentration of the iron atom in the vapor based upon its absorption of light. And in this case, we're going to be working down in the ultraviolet or UV part of the spectrum. Okay, so that's light we can't see. All right, so we're going to be comparing and contrasting standard curves and analysis using those two different techniques. Well, let's step back a little bit and talk about this business of how light interacts with matter. So you guys already kind of know about this because you studied it back in bonding. And you also talked about it earlier in dynamics when you talked about complexes and complex ions, because remember you said they're brightly colored and they absorb light. And we can calculate the wavelength we see and also calculate based on that the wavelength that actually gets absorbed. So you guys probably remember using the color wheel to do that. But let's kind of go back to looking at light in general. So this goes back to what we learned in bonding. Okay, so we can model light two ways. Light, as you guys remember, can be modeled as a wave. But you also remember that it might be modeled as a particle. Anybody remember what you call a particle of light? It has a name?
A photon.
Photon. Good. Good. So whether we model light as a wave or as a photon type particle depends kind of on the application or well, I should say the theory or the application or what we're trying to do with the light, how we're trying to model how it interacts with matter. That's probably the best way to look about it. So let's look at light from a wave-like perspective first. So if I think about it as a wave, I think about it as kind of a sinusoidal wave. That's sort of what a wave is by definition, propagating through space. So it's a moving wave. Okay, so you can think of it as like a wave in the ocean, right? So it's not a static thing. A wave of water in the ocean is constantly moving, right? So it has a rate or velocity at which it propagates. And we can think of light as the same sort of thing. The thing is that light propagates at a constant rate or velocity in a vacuum. And that's called the speed of light, which we're going to represent as c. And c is going to equal to, sorry, it's 3.0 times 10 to the 8th meters per second. So that's how fast the light wave is moving through space, if you will. Okay, its rate of propagation. Now, what are some other things that we could talk about in terms of characterizing light that happens to be moving through a vacuum like this? What other things can we say about it? What other properties might it have?
Wavelength.
Yeah, we can talk about the wavelength of it. So the wavelength is represented as lambda. Again, you guys learned this back in bonding. And it's going to be the peak-to-peak difference or valley-to-valley difference. So it's going to have units of length or distance like meters or centimeters or micrometers or nanometers or something like that. What's the thing that kind of ties wavelength and speed of light together? There's one other thing we can kind of talk about. Does anybody remember what it is?
It's not time, is it?
Not time, but it's close to that.
Frequency.
Frequency, yeah, that's the other thing. Okay, and frequency is given the symbol of nu, which kind of looks like a funny V like that. And frequency is equal to C divided by lambda, okay? So you can think about C, which is the speed of light, as being sort of the proportionality constant that relates frequency and wavelength to each other. And the other thing to remember about this is that it's an inverse dependence, as you see here. So the frequency goes up as the wavelength goes down. In other words, as the wavelength gets smaller, the frequency gets bigger. Okay, and you can kind of see that, right? Because if I were to compare two waves of light, hey, what if I put another wave underneath this? I'll make the amplitude a little different, but that doesn't matter. Obviously, the one at the bottom has a higher frequency. Now, if they're both moving at the same speed, right? Frequency is basically how many peaks are going to pass by me per unit time, okay? So it's kind of like standing like on the edge of an interstate or on an overpass and counting the number of vehicles that pass by you per unit time. So you might count the number of vehicles that pass by you per minute, right? So that might vary depending upon what interstate you're on or what time of day it is or something like that. So you're doing the very same thing here. You're basically standing on an overpass and you're watching a wave of light pass by you. And every time a peak comes by, you're counting that, okay? And you can see in the bottom case here, more peaks are going to pass by you per unit time than in the top case, right? Because the peaks are kind of shoved closer together. Okay, so the bottom one would be a higher frequency wave and the one on top would be a lower frequency wave. So notice again, as the wavelength gets smaller, the frequency gets bigger. And we relate the two through this equation. Nu is equal to C divided by lambda. Okay, so that's all stuff we do back in bonding. Everybody kind of sort of remember that?
Yep.
All right. And units of frequency, by the way, are going to be time units. So your units here would equal to events per second or peaks per second. So it's usually a time unit in the bottom. Okay, where the event doesn't really have a unit, so it's 1/seconds, so inverse seconds. And we also refer to that as hertz. So hertz is an inverse second. So it's events or peaks per second. All right, everybody see that?
Yep.
All right, good. So now let's talk about light in terms of it being a particle. That's the photon model. So in this case, we actually think of a light as being like a little particle or a bullet or something like that moving through space, right? And when we think about that, a particle moving through space is going to have kinetic energy associated with it, right? It's moving energy. Now, that's kind of a weird thing to think about because when we talk about light, we don't usually think of light as having mass associated with it. But then Einstein showed that mass and energy are interconvertible, equals mc squared, right? So essentially we can say that even though light doesn't have mass, we can treat it as a particle that does have mass. So in terms of an equation here, what we find is that the energy of the photon is equal to another proportionality constant, h, which is Planck's constant, times nu, which is the frequency of the light. Okay, so the h here is this thing called Planck's constant. And that's what, 6.626 times 10 to the minus 34th. It's in units of joules times seconds, where a joule is an energy unit, right? 6.626 times 10 to the minus 34th joule seconds. Now, if you wanted to, you could convert this back into wavelength type units as well, because you know that nu is c over lambda. So you could also say that E is equal to h times c divided by lambda. And that puts the energy of the photon in terms of the wavelength, which is sometimes convenient to do. Okay. So again, these are two useful relationships that we can have when we talk about the energy of light. So we can think about the energy either in terms of frequency, right, because they're proportional to each other if we're using the wave model, or in terms of the actual energy of the photon if we're talking about the particle model. All right, everybody good with that? And again, this is stuff you probably learned back in bonding last semester or whenever you took it. All right. So the next thing we kind of have to think about here is the so-called electromagnetic spectrum. So when we talk about the electromagnetic spectrum, we're talking about all the different kinds of light or electromagnetic radiation that we can actually have. I actually have the picture from your book that sort of shows this. So I'm just going to kind of show it as sort of a number line here. So much for my ability to draw a line here, but that's just not going to happen. So way down on the short wavelength end, okay? So this is small lambda here. And way up here, we're going to have large lambda, long wavelength. Okay? We're going to have things like X-rays. Okay? There are other ones as well, but I'll just kind of notice some of the ones that we're well familiar with. Then past X-rays, as we move longer in wavelength, we get to the UV or ultraviolet part of the spectrum. Then from the UV, we get to the visible part of the spectrum. And that's the part that we really care about for the most part in this experiment. Then beyond that, we go to the infrared. And then beyond the infrared, we have like the microwave and the radio. Wave parts of the spectrum. Now, the parts that we really care about here is for us here in the visible part of the spectrum, is that's going to stretch roughly from about 400 nanometers in terms of wavelength up to about 800 nanometers. Okay, that's going to be your Roy G. Biv, right? So your violet, your indigo, your blue, your green, what is it, yellow, what have I missed, Roy? I'm going Roy and Yeah, there it goes. Roy G. Biv in reverse. Okay. So your reds are up around 800 nanometers, your violets down around 400 nanometers. So those are all the various colors that you see in the rainbow. Okay, so everybody's kind of familiar with that. Okay, and then down to the UV, that takes me down to maybe about 190 nanometers. Okay, and that's of course light that's short enough wavelength that we can't see it. So that's, for example, the kind of radiation that will give you a sunburn. Okay, it actually can burn the skin. And then, of course, as you move down below that, you start moving down into the X-ray region. That's penetrating light, right? So that's light that can actually penetrate through soft tissue and skin, and it gets absorbed by bones. And that's why you can get an X-ray image of bones, because the X-rays can pass through the soft tissue, but get absorbed by the bones. And you see that contrast image in an X-ray, okay? And infrared radiation going in the other direction, that's thermal radiation, that's heat. Okay, so we can feel it, but we can't see it. And then microwave radio waves, we're talking about longer wavelength radiation that's used for communication. All right, so that's more or less what I'm talking about. Now, here's the thing to remember. The small wavelength, the short wavelength stuff is down at the left, the long wavelength is at the right. Okay, but what about frequency? Okay, if I were down at the left, down around the X-rays, would that be a small frequency or a large frequency down at the left by the X-rays?
It'd be large, wouldn't it?
Yeah, large frequency. Because remember, frequency and wavelength are inversely related to each other. So then I would have a small frequency down at this end. Okay, and what about the energy of the photon? Would the high energy B photons be at the left or the right? So how about energy? Where should energy be high, at the left or the right?
The left.
Mm-hmm. Yeah. All right. So there you go. You can actually see what's happening there. If we go from a small frequency to a large frequency, we go that direction. Low to high, we go in that direction, right to left. But for wavelength, we kind of go the opposite way. From small to large, we go left to right. Okay, so you can see those inverse dependencies that we have, that we've talked about. Okay. Now, for us, the important thing is, okay, so let's say I've got an atom or a molecule and I shine a particular type of light at it. Why does that light get absorbed? We know that happens, right? We know that atoms and molecules can absorb light because we learned about that back in bonding. We also talked about it in dynamics when we talked about how complexes and complex ions interact with light. So we know that matter can absorb light. So if I'm talking about atoms or molecules, and we're talking about, say, absorption in the ultraviolet and visible part of the spectrum, which is really the part that we care about here, what's actually happening? Why is the atom or molecule absorbing light in those regions? What's happening to the atom or molecule when it absorbs, say, a photon of visible or ultraviolet light? Anybody remember?
It promotes an electron to a discrete higher energy level.
Yeah, that's exactly right. So if we absorb UV or visible light, okay, what we're really doing is we're promoting electrons to a higher energy level. Okay, so if we're talking about an atom, for example, they have got, for example, low energy, higher energy here. Now, what do these actually refer to? Well, these refer to orbitals, don't they? Because that's what energy levels in an atom are. Okay, so for example, it might be, say, a 1s orbital and a 2s orbital here. Okay, so I might have an electron down in a 1s orbital, and if a particular photon of light of the right energy or frequency comes in, okay, I can promote that electron up to the next orbital. Okay, and those are atomic orbitals we're talking about there. okay? But the thing to remember, and you probably remember this from bonding, is that the photon energy has to be exactly equal to the energy difference between those two levels. If it isn't, then nothing happens, right? And that goes back to that idea that light is quantized when we talk about atoms and molecules. So in other words, only very specific wavelengths, frequencies, and energies of light can be absorbed by a given atom or molecule. So that energy has to correspond to a very specific energy level difference. Everybody kind of remember that as well?
Yep.
Okay, good. And if we're talking about a molecule, it's the same kind of thing. Okay, but now these happen to be molecular energy levels. Okay, so we might call this, say, a sigma level or a pi level. And these are defined, for example, by molecular orbitals and molecular orbital theory, which you guys may not have seen yet. But it's the same basic idea. Okay, an electron might be in a pi, say, bonding orbital, and it might get promoted to, say, a pi anti-bonding orbital. So I can put a star up there to represent that. But the same thing is true. In other words, we have to have the correct energy, frequency, or wavelength of photon being absorbed to cause that transition to occur. It's just that it's a different kind of energy level because now we have a molecule and there are bonds involved, which we don't have in the case of an atom. But in terms of what's physically happening, it's exactly the same process. Okay, so that's what's happening with regard to the kind of light that we're going to be focusing on in this lab. Now, other things happen. For example, if you're in the infrared part of the spectrum, we're causing bonds in molecules to vibrate. And if we're in the microwave region, they rotate end over end. Actually, by the time you get down to X-rays, that's high enough energy that you actually break chemical bonds. So it's called ionizing energy because it breaks bonds and actually kicks electrons out of atoms. So different things can happen depending upon what energy of photon we're talking about. But for the ultraviolet and the visible parts of the spectrum where we happen to live in this experiment, we're talking about electronic transitions. All right, any questions about that, guys? And again, I don't think I'm telling you anything new here that you haven't already seen before. Okay. So the other thing to kind of remember here, so let's just sort of focus here on visible spectroscopy, and the same stuff really kind of applies to ultraviolet. But this is kind of tying back into what we learn about, for example, complexes and complex ions. I'm going to tie that in here because we're actually going to end up making a complex ion. So if we have, for example, this one, here's a complex ion we can make. FeCN taken 6 times with 4- charge. So this is what I think the iron 2 one. So this is the iron 2 complex. So if I make up a solution of this and make it aqueous, it's going to appear pale yellow. So I might ask you then, okay, well, if it appears pale yellow, that's what we see. What color is getting absorbed? Anybody remember how we do that? How would I determine the color that gets absorbed if the complex ion appears pale yellow?
You would look at the opposite color on the color wheel.
Yeah, so we would make a color wheel here. I do simple color wheels that only have like 6 segments in them. Okay, so we can actually do red, orange, yellow, green, blue, violet. I left the indigo out. So we look for the complementary color, right? So if we see yellow, we go across the color wheel, and that means we absorb violet, okay? So we always absorb the complementary color to what we see, and the complementary color is the color across from the color we see on the color wheel. All right, so everybody kind of sort of remember that. So what this tells me is that I'm absorbing violet light. Violet light is fairly energetic light. It's closer to the ultraviolet part of the spectrum. So what does that tell me about the energy gap that I have to cover, which is kind of that delta in the d orbital splitting diagram? Is it big or small?
Small.
Yeah, actually, it's going to be big because violet is a cool color. Remember, cool colors are what? Short wavelength. Short wavelength means high frequency. High frequency means big energy, right? So that tells me that delta gap in the crystal field splitting diagram has to be big. Okay, so you guys kind of sort of remember that from earlier in this semester. All right. So what kind of an instrument do we use to actually make these measurements? So normally when we do this with the aid of an instrument, we're not looking at the wavelength or color that we see. What we're doing is we're focusing on the wavelength or color that gets absorbed. Okay, so what we do is we use an instrument called a spectrophotometer. All right, and what a spectrophotometer does for us is it allows us to measure the absorbance of light at a given wavelength. All right, so inside the spectrophotometer, we usually have the ability to set the wavelength. And once we set the wavelength, we have the ability then to measure the absorbance of light for a particular analyte at that wavelength. Now, what do I mean by absorbance? Well, when I talk about absorbance, what I'm talking about is the amount of light that gets absorbed. Because remember, that's complementary to what we see. So we're really focusing on the absorption part here. Okay, so let's actually take a look at a simple block diagram of a spectrophotometer. In other words, these are the parts that we would see in the instrument if we could take it apart. Okay, so this would be the simple Spec 20 that I'm talking about. Okay, so what we would actually have here, and we'll go back and talk about each one. And I usually do this according to what I call a block diagram. And if you take me for analytical, we always kind of start out our discussion of an instrument with a block diagram that lets us see the individual parts of the instrument. And then we kind of delve into great detail about what each one does and how it does it and all that good stuff. So we need to have what's called a white light source. Now, when I say a white light source, what I mean is a light source that contains a wide range of wavelengths. Okay, so if I have a visible source there, we're going to say that it's going to cover all of the different colors or wavelengths of the visible part of the spectrum. A good example of this would be a tungsten bulb. So that's just your good old-fashioned light bulb, right? So it gives you what we call white light, which actually contains all the different wavelengths in the visible part of the spectrum. Plus maybe a little bit down into the ultraviolet and certainly some up in the infrared, because when you feel around a light bulb, it gets hot, right? So what's going to be coming out of this is going to be light, which we represent as h nu, but it's going to have a lot of different frequencies or wavelengths associated with it. Now remember, the goal of this is to measure the absorbance at a given wavelength. So the next thing I'm going to need here is some sort of a wavelength selection device. Okay, now you guys have all seen a wavelength selection device before. You ever played with a prism before?
Yes.
Yeah.
Yeah, so okay, you take sunlight, which is white light, you shine it through a prism, what do you get?
A rainbow.
Yeah.
Yeah, you get the rainbow out, right? So the prism takes the sunlight, which is white light, so it's all the different wavelengths combined, and it disperses it or separates it out into its individual colors. So you see all the different colors of the visible part of the spectrum. So you can thereby in space essentially separate out blue light from green light from yellow light from orange light. That's what a rainbow is, right? So that's what the lambda selection device is. So we'll just say for grins and giggles here, this is a prism. And actually, in the old spectrophotometers, that's what they used. Now we use something called a diffraction grating. Okay. So now coming out, what we're going to get is a single wavelength or frequency. So I'll call that an H nu 1 to show that it's a very specific frequency or wavelength coming out. Okay. So now what we're going to do is we're going to pass that through our sample. Now, another thing to keep in mind here is that the light coming out of the wavelength selection device is going to have a specific intensity associated with it. Now, what's intensity? Well, that's the brightness of the light, right? So you guys know the difference here. I can have bright light or dim light. So I can have a red light that's really dim, and I can have red light that's really bright, right? Now, they're both the same energy. It's just that the amplitude of the wave is different. Okay, so there's more intensity. So you know what I mean by that. You know what the difference between an intense red light or an intense blue light versus, say, a dim blue light or a dim red light would be. So that's what that I is. That's intensity of light. So we're going to pass light with a given intensity through the sample. Now, presumably what's going to happen is the sample is going to absorb some of that light. So I'm going to have an intensity at a given wavelength coming out of the sample. It's the same wavelength as I had coming in, but the intensity is different because now presumably the sample has absorbed some of the light, right? So what I can say here is that the intensity coming out is going to be less than the intensity coming in. Okay, and that makes sense. That's what absorption of light is all about. So now what I'm going to do is I'm going to place on this side something called a detector. Now what the detector is going to let me do is actually determine quantitatively what the intensity of the light looks like, okay? So it can allow me to differentiate between an intense amount of light and a not so intense amount of light at a given wavelength, okay? And the way it actually does that is it converts the energy of the light through its intensity, okay, over to actually an electrical quantity like a current or a voltage. So if the intensity gets bigger, the current or the voltage also gets bigger. If the intensity of the light gets smaller, the resulting current or voltage coming out of the detector also gets smaller. Okay, so intense light gives me a larger voltage or current. Less intense light gives me a smaller voltage or current. Okay, so I have a way of quantitatively determining the intensity of the light and comparing one intensity to another now. And then, of course, from the detector, I have to get to some sort of a readout or readout device that tells me either what the intensity of the light is or it converts it directly to an absorbance. Okay, so does that kind of make sense to everybody? And by the way, if we're talking about a liquid sample, we usually put it in some sort of a holder called a cuvette, and you'll see what those look like tomorrow. All right, so that's what we have in terms of an actual spectrophotometer. And remember, the goal of this is to measure intensities. And if I want to actually make a comparative difference, I need to know both I naught and I. And the difference between those two ought to be the amount or intensity of light that gets absorbed by the sample. All right, so those are the two things that I need to be able to actually measure. And I can do that, for example, by either having the sample present, at which point I measure I, but if I take the sample out, I measure I naught. Okay, and if I have both of those, then I can get the difference between them. Okay, does that make sense to everybody so far?
I have a quick question.
Sure.
Sorry, what does that last box say?
Readout.
Okay, thank you.
So that would be either an intensity readout and counts, or it would be an absorbance. And the absorbance can be obtained from the I and the I naught. All right, so let's just define this I business. So I, if I define it in general, is going to be the intensity of the light. And I can think about it as the number of photons of light striking a given area of detector over a given time. Okay. So that's what intensity is. Now, again, I have two variations of this. I have I naught. I naught is the initial intensity from the source. And then I have the I. And that's the intensity after passing through the sample. As a general rule, as I mentioned, I should be less than I naught if the sample is actually absorbing light at that wavelength. All right, everybody good so far with this? All right, so now the question becomes, all right, so if I can measure these intensities, what I'm really trying to get at is the absorbance, right? Because the spectrophotometer, as we said, measures the absorbance of light at a given wavelength for a given sample or analyte. So the question is, how do I relate these intensities back to the amount of light that gets absorbed? Well, here's how we do it. Okay, we have to start out with a few terms here. So the first term we start with is something called transmittance. Pardon my handwriting there. Transmittance. And what transmittance is the ratio of I to I naught. Okay, so if I is equal to I naught, okay, that means the transmittance is 1, okay, which means that 100% of the light's getting through. Okay, another way I could actually state this is as percent transmittance. And that's just equal to the and by the way, transmittance is given as a capital T. Percent transmittance is just that ratio, I over I naught, times 100. So I'm just representing it as a percent instead of just as a number, okay? Now, here's the deal. If I can measure this transmittance or percent transmittance, now what I can do is take that back to the quantity that we really care about, which is absorbance. Now this is the amount of light that gets absorbed. Now absorbance is given as capital A, and it's equal to this. It's equal to the log, it's a base 10 log of I naught over I, which is kind of like 1 over the transmittance, right? Or if I wanted to get it in terms of transmittance, I could call it the negative log of I over I naught, which is just equal to the negative log of the transmittance. Okay? So now what you see is I have a means of being able to, from I and I naught, determine the amount of light that actually gets absorbed by a sample. Okay, and that's ultimately what we want the spectrophotometer to us. Now you might ask at this point, well, why use absorbance? Why couldn't I just use intensity straight out or just use transmittance or something like that? Why use absorbance? Now the reason why I use absorbance is because ultimately in an analytical measurement, what am I trying to get back to? In a quant measurement, what am I really always trying to get back to? What do I want to know about the analyte in a quant experiment?
Concentration.
Concentration. I want to know how much is there, okay? And absorbance is good because it relates directly to concentration. So that's why we like to measure it. And it does this through something called Beer's law. Spelled like the beverage. It's actually called the Beer-Lambert law, but usually it gets shortened to Beer's law. And here's what it says. And here's the useful form for us. It says that absorbance is equal to this term called epsilon, which looks like an E, times a lowercase b times a c. All right, so here's what all these things are. Okay, we'll start with the obvious ones first. C is molar concentration. Ooh, that's what we want to get, right? B is the path length of the light through the sample. So you can imagine it this way. If I've got the actual sample as a liquid in some sort of a sample holder, like a test tube, okay, and I'm passing light through it. So got light coming in at an intensity I and it's coming out at an intensity I naught. Okay. This gap or distance that the light passes through inside the test tube is the path length. Okay. And you can see what happens. It kind of makes sense. If I used a fatter test tube, right, then the light has to go through a longer path length, doesn't it? And if the path length goes up, there's more molecules or atoms in there to do the absorbing. So it makes sense that the absorbance ought to be proportional to the path length. And then finally, I've got this epsilon term. This is called molar absorptivity. Now, the one thing we haven't really talked about here is the ability of the thing that's doing the absorbance. Let's say it's a molecule or a complex ion or something like that. We haven't talked about the ability of the molecule to absorb light at a given wavelength. Okay, well, a couple things happen. Some species, molecules, complex ions, atoms, whatever it is we want to talk about, are just better absorbers of light than other things are. And there definitely ought to be a wavelength dependence there. Okay, some things absorb really well at short wavelengths, other things don't. And vice versa, some things tend to absorb better at longer wavelengths and other things don't. So usually we have to think about how well a specific molecule or species is absorbing light at a given wavelength. And that's what the molar absorptivity tells us. Okay, so the molar absorptivity is the ability of an absorbing species to absorb light at a given wavelength. Okay, so for example, if I just have the iron ion by itself and I just put it in liquid solution, aqueous solution, it doesn't absorb very well in the visible part of the spectrum. It doesn't absorb at all. And you guys will see that tomorrow when we give you your unknowns that have iron in them. You're going to hold that up, and one of the observations you're going to make is that the solution is clear and colorless. So what that tells you is that iron ion does not absorb in the visible part of the spectrum. That's a problem if you're doing visible spectroscopy with it, where you're working in the visible part of the spectrum. So what do you have to do? Well, you got to make it absorb, right? So the way we're going to make it absorb is we're going to use that iron ion and we're going to make a complex ion out of it. And guess what? When you make a complex ion out of it, we can make it absorb light really well in the visible part of the spectrum. So what we're doing is we're enhancing the molar absorptivity by converting the iron ion into an iron complex ion. Okay, so now it can absorb really well in the visible part of the spectrum. Okay, so that's what we're trying to do. Let's just do a real quick thing with Beer's law here. Let's see if we can get the units on molar absorptivity. So remember that A is equal to epsilon times B times C. We want to solve for epsilon and stick units in. So that's absorbance over B times C. Okay, so we got to think about what all these units are. B is path length. We usually would measure that in terms of centimeters. C is molar concentration. So that's going to be in terms of moles per liter of solution, right? What about A? A is absorbance. Let's go back and look at what absorbance is. Oh yeah, here it is. It looks like it's a log of an intensity ratio. So what sort of units should absorbance have?
No units.
Doesn't have any units, because first of all, you're looking at an intensity ratio. So if you're using lumens or whatever, they're going to cancel out, right? But we also know that anytime we take a log of something, okay, the log quantity has to be unitless. Okay, so in this case, absorbance is unitless. So we can see it as liters per mole times centimeter. So either way gives you appropriate units for molar absorptivity. Okay, does that make sense to everybody? All right, so let's go back to our situation so we can call it a day. I mentioned to you that our analyte is iron 2+. Okay. The other thing I mentioned to you is that it is colorless. Not very useful to us if we're doing visible measurement. So here's what we're going to do. We're going to put a ligand in there. And the ligand we're going to use has the formula of C12H8N2. Okay? It's actually called 1,10-phenanthroline. It's an organic ligand. It's bidentate. Kind of like ethylene diamine is. So if I have 3 of them, I can take up 6 coordination sites around the iron and I can make a complex ion that looks like this. By the way, it's a neutral ligand. And the whole thing is going to carry a 2+ charge because of the neutral charge on 1,10-phenanthroline. And here's the cool thing. It's an octahedral complex. And like lots of complexes or complex ions, it absorbs light very readily in the visible part of the spectrum. So it appears deep orange. So that's the trick that we were able to use. I was able to take something that's our analyte that would otherwise be colorless and unable to be viewed in the visible part of the spectrum, and I turn it into a complex ion. And now I've totally changed its electronic properties so that now it can very readily absorb visible light, and it appears this really pretty reddish deep orange. You'll see it tomorrow if you haven't seen it before. It's very, very nice. Okay. And what we're going to do tomorrow, among other things, is we're going to measure the wavelength of maximum absorption. Okay. And the reason for that is because that's going to allow us to make the most sensitive absorption measurements if we're at the top of the absorption peak. Okay. So that's one of the very first things we're going to do tomorrow. Then once we have that wavelength, then we can turn around and apply it to a series of standards. And we're going to make a standard curve, kind of like we did in the kombucha lab that you guys turned in a week or 2 ago. And we'll work from there. All right, so I think that gives us enough of a background to kind of appreciate what we're doing tomorrow, and we'll talk more about it on Wednesday to kind of finish it out. But any questions as of now about sort of where we're going and what we're trying to do? All right, everybody good?
Yep.
All right, guys. So I'll see you tomorrow. Looks like we're definitely there. We're at 20 after. So I will see you guys tomorrow at 5 o'clock. Hopefully everything will be prepped and ready to go, as we say. All right, we'll see you then, guys.
Have a good one.
Thank
You
you.
too.